upload new notes, so you can go ahead and take a look at those. We are going to finish up this unit by talking about language, but before we get to language, we're going to talk a little bit about logic and reasoning. And I will mention to you that this is probably going to be one of the hardest sections to kind of wrap your head around. You'll notice in your syllabus for the week that we are doing logic and reasoning, I want you to read a lot of McRaney, because McRaney talks about a lot of different logical fallacies that you will encounter. Some of these can be found on the internet. So if you go to an internet comments section, you will usually see a lot of different types of logical fallacies and things like that. So make sure you take a look at that. Just a friendly reminder that that homework assignment that we moved, that will be due on Friday. So I will take some time at the end of class to kind of talk about what I want you to do for this. It shouldn't take you very long to think of an alternative, I hope. So when we talk about logic and reasoning, so we are kind of jumping around a little bit. This is basically the back half, chapter 10. What I never really understood, it used to, in the previous edition, it used to be its own chapter, but they've kind of moved it into problem solving. So we're still kind of stuck in chapter 10. But there are two different types of reasoning that we are going to talk about here. Now, the first type of reasoning is what is called inductive reasoning. So this is basically, we draw a generalized conclusion, and we're going to use this word a lot, a premise or a statement that refers to a particular instance. And so we have premises, we have statements, and we come to a general conclusion. So we're basically going from specific to general. Now, the conclusions are probable, but they are not always taken to be true. Now, here's a question that I have for you. Can anybody look at this type of reasoning and see something kind of similar that we do all the time? If you're in research methods, this might actually be pretty easy to notice, maybe a little bit. So what do we do when we're in a research study? So we look at specific data from a specific sample, and then we try to generalize to the larger population. So a lot of research that we do makes use of inductive reasoning. Does anybody have any other examples of inductive reasoning? So hypothesis testing is a type of inductive reasoning. Can you think of any other examples? Any other examples of inductive reasoning? Yes, Sarah.
Would it be like trying to figure out someone's like dialect?
How so? So we're kind of moving from specific to general, so specific instances to general conclusions. So how would that work?
A dialect in Spanish, but it's Spanish instead of English.
Can you give me more?
So
I don't quite understand.
Oh no, I feel like it's here on, but wouldn't this be like all the different types of English, just saying it's English, but there's little parts?
Oh, so ignoring dialect and basically focusing on English. Okay, well, here's kind of another example. So I'm going to use annotate for this because I think you're kind of on the right track. So here's what was kind of popping in my head. Okay. Can you tell me what can you say the first word for me? Can you say the second word for me? Okay. Now, is there anybody here who says pin and pen the exact same way? Okay. So, for example, here we have specific instances of not mispronunciation, but different pronunciation. So somebody that says pin and pin, you'd probably notice from those specific instances that their accent is probably Southern. So it's a general conclusion based on specific pronunciations. Does that kind of help you? Because I think you had the right idea, so I was kind of jogging it there.
We're going for accent forgot the word.
That's all right. No, an accent is a dialect. That is totally fine. Any other examples? So your book has the example. This is something that you do all the time. You may have noticed that your colleague is always happier on Fridays than on Mondays. I would say this is also true for you as well. You tend to be much happier on Friday classes than on Monday classes. And we can probably draw the conclusion that you like weekends more than weekdays based on that. Now, that may not always be the case, but we're arguing from specific instances to general conclusions. In hypothesis testing in the sciences, we are always using inductive reasoning. So one thing to keep in mind with inductive reasoning is that our conclusions are not always true. They are just probable. So if you've had me for general psychology, or if you have me for research methods, one of the big things you're going to hear me say is, I don't ever want you to use the word prove. And that's because prove implies settled knowledge that is always correct. Anytime that we are doing hypothesis testing, we don't have 100% truth. The conclusions are more probable or less probable, but not true in all instances. As a result, we don't use the word prove. It's a dirty word, sort of. Okay. So something kind of related to now, on the other hand, we have what is called deductive reasoning. So deductive reasoning is a bit more complicated in this instance. So with deductive reasoning, we are drawing valid conclusions from a set of premises. So what separates this from inductive reasoning is that, folks, you are a lot less likely to do this in your everyday life. You're a lot more likely to use induction. We go from specific to general. On the other hand, with deductive reasoning, we are basically drawing valid conclusions from a set of premises, and we're often going to use formal logic. And most of the time, you and I do not use this type of logic in our everyday lives unless we are in a logic class. So sometimes this is referred to as conditional reasoning. We'll talk a little bit more about this. But one of the things I will say, this is probably going to be the hardest section to wrap your head around, because when we're talking about deductive reasoning, here's what's really important. The content does not matter. It is the form of the argument that matters. So the conclusion validity in this case is when the conclusion follows naturally from the premises. The conclusion does not have to be true in real life. It just has to follow from the premises. So I'm going to give you an example. Okay, so we're going to try this and you can have a laugh at my expense. If there is meatless chili today, then ghosts exist. Exit. There is meatless chili today. Therefore, ghosts exist. So is this last one true? Well, we don't know. Some of you will say yes. I will say no. I will tempt fate and say no, they don't. But we don't have a statement of truth. However, this conclusion is valid. Do you know why? It naturally follows from the premises and it is in a proper form. When it comes to deductive reasoning, this is going to be the really hard part. It is not the content that matters. It is the form. This is in a valid form, which means that it's valid. Now, how many of you do stuff like this in your everyday life? Okay, a few of you, but most of the time we're going to be using that inductive reasoning. And oh, I'm going to have another. Thank you. Okay. So one thing I will mention, this is the part where I mentioned that I was a philosophy minor. I was actually required to take logic as part of my minor, and logic is probably one of the classes that I use in my everyday life the most, because it really comes into play when you're doing things like computer programming. Okay, so we'll talk a little bit more about each of these in more detail, but we're going to start by talking about inductive reasoning. So most of our reasoning is inductive. As I've kind of mentioned, a lot of our inductive reasoning comes into play when we are talking about testing hypotheses around the world. And that includes scientific reasoning. So basically, I have a hypothesis for how I expect the data to go. I collect my data, and then given the data that I have, I figure out which is more or less likely to be true given the data that I have. Is it the null hypothesis, or is it my alternative? Now, you and I do a lot of informal hypothesis testing in everyday life as well. So for example, I know not to necessarily introduce intense information the day after an exam. And yet here I am doing it. Because I know your brains are going to be a little bit fried. Like generally the class after an exam is pretty low energy. Also, we're in the middle of November. It's already low energy enough. Don't worry, I've got enough energy to help you out. I got enough energy for all of y'all. I got this. But when we're talking about hypothesis testing, Karl Popper, who is a famous philosopher who focuses on the philosophy of science, says that when we're testing hypotheses, we should be looking for what we call falsification. We should be trying to prove a hypothesis false. So if we want to test a hypothesis, we need to think about what would make that hypothesis false and test it against that information. It's part of the reason why, if you're doing things like null hypothesis testing in scientific research, you're always trying to falsify your null hypothesis. You're always trying to say, you're always planning to reject your null hypothesis. And you have to have enough data to reject that hypothesis. We should focus on proving our hypotheses false to see if they hold up and stand to scrutiny. But what's interesting is that when most of us get a hypothesis in our minds, we seek evidence to confirm our hypothesis. We do not seek evidence to disprove our hypothesis. So we're going to try an example, and y'all are going to hate me. This one's tricky. If you've heard about this already, don't spoil it for anybody else. Now, when we talk about confirmation, we are obtaining evidence that confirms that a hypothesis is correct. If we're talking about falsification, we are attempting to prove our hypothesis false through various types of tests. So for example, if I believe that my new car that I've designed can hold 900 pounds of weight, you know what I should do? I should put over 900 pounds in there and see if my car can still operate, right? I should put weight in the car, test it over 900 to make sure that it actually can hold up to 900. So we need to try to falsify rather than confirm. All right. Everybody got this down? Few more seconds? That's fine. More time for caffeine. Yeah, I was going to say, I'm too far away. I'm too far away to get it. All right, everybody good? Okay, so we're going to try something. I am going to present you with a sequence of 3 digits that are organized according to a rule that I know, but I'm not going to tell you. What I want you to do is I would like you to generate a set of 3 different numbers to test the rule. And then if you think you know what the rule is, you can tell me. So I will tell you if your set that you generate fits the rule. And I will also tell you whether or not the rule that you came up with matches my rule. Okay, so if you already know this, don't spoil. My digits, my rule is in my mind, and here are 3 digits that conform to my rule: 2, 4, 6. So now what I'd like you to do is try to figure out what my rule is and try to come up with a sequence of 3 digits, and I'll tell you if it fits my rule. And then if you wish, you can tell me what you think the rule is. Does anybody have a thought? Somebody's got to give it a shot. Yeah, Allie. That does fit my rule. What do you think the rule is? That is not my rule. Okay, somebody else. Sarah. No.
About squares.
Evens? No, that's not my rule. Allie. That is not my rule. Somebody want to generate some sequences? Maybe that'll help us figure it out. So give me 3 digits that you think fits the rule that you have in mind. Or you can try to falsify if you'd like. Because so far, any digits that y'all have given me fit my rule. Yeah.
Does 1 fit in your rule?
I need 3 digits. That will not work.
14, 16.
That fits my rule. What do you think the rule is?
You have to like, so it's like 1 and 1 makes 2, 2 and 2 makes 4, 4 and 4 makes 8.
That is not my rule. This is not a Fibonacci. Yeah, Nicole.
You're just putting it in a number sequence. Like you're just going up by number.
So can you give me an example?
So like 11, 12, 13. Like you're just going up.
That is my rule, but you want to know what I find real? So you just had to do increasing numbers. So 1, 2, and 3 fits the rule. But here's what happened. But here's first of all what I noticed. Every single one of you that generated a sequence sought to confirm what they thought the rule was. Nobody gave me a sequence that decreased. Nobody gave me a sequence that kind of was seeking to falsify the rule that they had in mind. Everybody sought to confirm. Now, this was a unique instance because Nicole got it right away while using a confirmatory sequence. Most of the time, though, when I do this, it takes forever because everybody's looking to confirm. Oftentimes, we're going to find with falsification, it's quicker. So if you thought that the rule was increasing, what you should have done is done like 15, 14, 13, which does not fit with the rule. So this is what is called the Wason 246 task, which is basically what I gave you. And Wason famously gave students the sequence like I gave you. And what he found is that in general, people use confirmation bias. They look for information that confirms what they already believe, and they do not seek to falsify their rule. They seek to prove their rule. So oftentimes they were generating a set of numbers that confirmed the original hypothesis that they already had. So what we find, you would think, here's what's interesting. So performance should improve when people are not seeking to confirm. So like I said, maybe we would have gotten the results a little bit faster if we had tried to falsify and not seek to confirm. But it turns out that not everybody finds this. So sometimes confirmation works. Oh, so I think we've talked about this. You and I have the exact same cardigan.
Yes. We have 2 of the same.
Yes, I know.
We have this one from Target.
Again, and the other one from Old Navy. I didn't mean for that to happen. I'm just cold all the time and I like neutral colors. I'm glad I wore a jacket today then. It looks better with my Blues jersey. And on Friday, I will be wearing a different Blues jersey. They finally started winning some games. What? I like sports.
No, you're good.
I'd still wear it even if they were losing. You know why? Because it looks good on me.
It just said the funny thing is that I've made that comment recently. To the team.
Hmm.
And my friends were back home and were like, shut up.
No, I definitely know a student who's a Chicago Blackhawks fan, and she's like, Dr. G, really? The Blues? I'm like, they're the home team, even though they're like 5 hours away. But I used to go all the time. All right. So surprisingly enough, it doesn't always help when we encourage people to falsify. So how do you get people to discover the rule? So what we find is that if you give people instructions to confirm, people do generate more test items that are incorrect. So possibly having people try to confirm the rule, what we do find is they get more information to help them make decisions. So sometimes instructions to confirm help because you can figure out what the rule is from negative tests as well. And instructions to confirm do generate more negative tests. Now, Clayman and Ha back in 1987 kind of said that, let's be honest, increase a set of 3 increasing numbers is too general. And so maybe part of the problem is that most of us are thinking of a more specific rule. And Clayman and Ha have actually found that when you make the rule more specific, people have an easier time discovering it. Additionally, Cherubini and colleagues in 2005 actually went one better. So 246 fits the rule. If I also told you that 579 fits the rule, maybe that would help. However, then you'd think, oh, it's increasing by 2s, and it's not. So having 2 examples actually helps you also more easily figure out the rule. So some of these things can be used to help you find the proper sequence. So make a more specific rule, mention additional examples that fit the rule. Sorry, I got excited. Okay. Everybody good? Lauren, do you need a little more time? Nicole?
No, I'm good, thank you.
Okay, so interestingly enough, you know who we should ask about inductive reasoning? Scientists, because they test hypotheses all the time. And what's interesting is that you would think that with scientists that they would be more likely to engage in falsification. No, not at all. Mytroff in 1974 actually followed up with scientists to see what they were doing. And in general, they found when it comes to inductive reasoning, scientists actually spend more of their time confirming their own hypotheses rather than trying to falsify them. What's interesting, though, they are more than happy to falsify somebody else's hypothesis. So remember, hypotheses are like toothbrushes. Everybody should have one, but nobody should share it. Now, one of the other things that we have found is that scientists are actually much more reluctant to abandon their hypotheses. And you might be wondering why this is when scientists are committed to this process of hypothesis testing. So here's the thing. Most scientists have some sort of pet theory or pet idea that they have about the world. They have spent years researching the phenomenon of interest. They probably have many publications that are based on this. They are trying to get grant money for this because publication and grants are how most scientists get to keep their jobs. So when you think about how much they put into their area of study, it's not that surprising that they're going to show greater commitment to a hypothesis than any random person on the street. They have greater commitment. And what's interesting is that if they do find disconfirming evidence, they are going to attribute it to measurement error. So what's been really interesting is that a lot of psychology studies do not replicate. Not all of them, but some of them do not replicate. And occasionally you will get somebody who says, I failed to replicate this study. And this person will basically be told the reason you didn't get it is because you did it wrong. So again, we're not really paying a lot of attention to that disconfirming evidence, and we need to be. Okay, everybody good? Okay, so should falsification actually be a goal for scientists? Karl Popper basically assumes that research can at least rule out a hypothesis, but falsification is often going to require more than just one study. To falsify a hypothesis, you need a proven track record of multiple studies that fail to find the effect. Now, researchers have also looked at simulated research environments with college students, and generally compared to science, compared to simulated research projects done with participants, scientists often have more commitment to their hypotheses than a bunch of participants who have been selected to take part in a research simulation. So obviously, it's not surprising that scientists would be more committed to their hypothesis than a bunch of randoms, obviously. But one of the other things that we do find is that oftentimes, if you are working in a team, whether that is in an established laboratory or in simulated research, having collaborators actually makes you more open to new ideas and less likely to doggedly stick with a research hypothesis. You okay? Okay. You were kind of pulling a face. I thought I had said something upsetting. I was like, what? Scientists are more committed to the hypothesis? How dare you? Scientists have to publish or perish? What? Oh. It might have just been your resting face. I have resting sad face. So when I don't smile, people are like, what's wrong? I'm like, I'm just not smiling. How many of you here have resting sad face? How many of you have resting bee face? Really, do you?
Well, I have a resting mad face.
Oh.
People will look at you and be like, are you mad? Or look at me and be like, are you mad? And I'm like,
Did I do something wrong?
look at my face. I'm just
What?
sitting there.
Okay. Right. Sarah, do you need a little more time? Okay. Okay. Let's talk about deductive reasoning, everybody's favorite. Yay. You're going to like some of the examples I picked here. So when we talk about deductive reasoning, there are a couple of different types of reasoning that we can do. So oftentimes, most deductive reasoning that you are going to see has logical operators such as or and if-then statements, as well as what is referred to as if and only if, which in logic looks like this. If. So additionally, the propositions can be either true or they can be false. However, when we talk about deductive reasoning, we are talking about the validity of the argument. Now, when we talk about validity in our everyday life, you'll hear me say things like, that's a valid point, or that's a valid argument. When we talk about this informally, basically what we're saying is, that's logical, that's a fair point. When we're talking about validity from a deductive reasoning perspective, we are basically taking the premises as true. And the question of validity is, if we take our premises as true, does the conclusion follow from the premises? So, for example, here are two premises. If meatless chili is on the menu today, then ghosts exist. Meatless chili is on the menu today. We have to take both of those premises as true if we want to judge the validity of the argument. the final statement of the argument is, therefore, ghosts exist. Now, if the premises are true, does the conclusion naturally follow? And in this particular instance, it does, not because of the content, but because of the form that the argument takes. So this is the part that's going to be really hard to wrap your head around. You can argue for anything, and it's valid as long as it's in its proper form. So one standard argument, the argument that I've just given you about chili, meatless chili, and ghosts is what is called a modus ponens argument. So it follows this form. So I realized this is how you would write it in propositional logic. So I'm going to write what this looks like in plain English. So here's the basic form of the argument. If P, then Q. P, therefore Q. So here's the really cool part. This is a valid argument regardless of what you fill in the blanks with. So somebody fill in these blanks and make me a new valid argument. So fill in the blanks for P and Q. Somebody try this for me. It can be as weird as you want it to be.
If it rains, then okay, scenario, someone's pregnant. If it rains tomorrow, you're having a girl.
It's raining,
It rains tomorrow.
therefore you're having a girl. Yep. So that's kind of how it works. Somebody else want to try? You can fill in anything you want.
I used to do this all the time, but they would always end up wrong. That's how I would think as a kid, like, I would go, if there are 4 dandelions at the base of the stairs outside, then my dad will give me dessert for dinner.
And then you did find that at the base of the dandelion, so therefore your dad will give you dessert. Now, it's okay, so it's a valid argument, but it may not be an accurate reflection of reality. But here's my point. This is not about reality, it's about the form of the argument. And this will always be a valid form. So, for example, if I drink a Mountain Dew in the next 5 minutes, we will not have class on Friday. I will drink a Mountain Dew in the next 5 minutes, therefore we will not have class on Friday. Now, are we going to have class on Friday? Yes. It was just an example. I'm sorry I got your hopes up, but it's a reminder, proper logical form, not an accurate reflection of reality. I mean, I feel like I owe you snacks now, or extra credit, one of the two. Snacks and extra credit? Maybe? Huh? You don't need to argue for that. I'd do that for you.
If we bring us snacks, then we get extra credit. Just bring it.
Bravo. I think you've totally understood this argument. So this is called modus ponens. I will. Okay, so I tell you what, who's going to be here on Monday?
I will.
Cool. I'll bring snacks. And even if you're not here for snacks, I will still give you an extra credit opportunity because I tricked you so hurtfully. I should watch my mouth.
I thought there was like a surprise person coming and I was like, Santa?
I was like, if I drink this in the next 5 minutes, BTS is going to walk through the door. They're not. Sorry. I'm sorry. Okay. All right. But does this kind of make sense? So you can basically fill in anything you want, no matter how nonsensical, and it's technically valid. Okay. I need to clear. There we go. Okay. And turn off annotate. Okay. So here's another logical form. This one is called modus tollens. So this is another valid form. Now this one takes a slightly different look. If P, then Q, not Q, therefore not P. So again, form is valid. You can fill it in with whatever you want. Somebody give me an example. Anything you want.
you bring a snack to get extra credit. but we
I-
don't get that extra credit, therefore we don't get snacks.
Yeah, exactly. You can fill it in with whatever you want and it's still a valid form. Now, some of you might be wondering, why is this valid? Wouldn't it be just as valid to say if P then Q, not P, therefore not Q? Not exactly. So the if here does not mean if and only if. So that's really important here. It just means if, not if and only if. And we'll talk about those invalid logical forms in a minute. I want to skip ahead though, because I want to show you the Wason card task so that you can kind of understand this next part. So I'm going to jump around a little bit for this. You need to know these two logical forms to be able to do the Wason task. We've got 10 minutes, so I've got time to cover it.
Oh, that's not what I was looking at.
Okay.
Yeah.
So I'll come back to this. I'll come back to all of this. Okay, so you're going to have to make a mock-up of this in a second for Friday, but I want you to use rules that make sense. But right now, here's our rule. If there is an R on one side of the card, then there is a 2 on the other. Which cards do you turn over to determine if the rule is correct, not direct? So here's a really easy way to think about this. This first argument that I'm making is if R, then 2. So here's my question. What two cards, which card? So you don't have to turn over 2. You can turn over more if you want. But what cards do you want to turn over to determine if this rule is correct, knowing that we're basically taking the conditional rule if R, then 2? So we should probably turn over R, right? What else do we want to turn over? You want to turn over 2? Are you sure? Anybody have any other ideas? Sarah, what do you want to turn over?
R and 7.
Okay. So, and some people want to turn over 2, but really you only need to turn over 2 cards. You only need to turn over R, and then you need to turn over 7. Now here's why. So if we think about this in terms of modus ponens, so remember modus ponens was the rule if R then 2, R, therefore 2. Go back to your notes. So we should flip over R. That is modus ponens. However, here's the thing. I did not say if and only if there is an R on one side, therefore there must be a 2. So you could flip over 2 and there does not necessarily have to be an R on the other side. What we need to do is 7. Why 7? Because it's not 2. And if it's not 2, therefore not R. That's modus tollens. So that's how we only need to flip over 2. So the thing is though, when you look at this rule, it's really hard to understand, isn't it? So this is hard. You should pick R and 7, but most people either just pick R or they pick R and 2. When you think about this in terms of modus ponens and modus tollens, you actually have an easier plan. The task has been argued to be too abstract. And I will go over the notes on this in more detail so you don't miss them, but I want to show you this. I want you to come up with a real world example like this that makes it easier. So this comes from Cosmatos and Tooby back in 1992. If you are drinking alcohol, then you must be over 18. Which card should I pick? I should pick the 16-year-old, so not 18, and I should pick the beer. That's a little easier to understand when the rule is in everyday life, right? You don't care about who's 25. You don't care about the soda. So here's what you have to do for Friday. I want you to use an example like the Wason task where you have 4 cards, and you need to have a rule like this that makes it easier for you to process. And remember that we need to always flip over 2 in accordance with modus ponens and modus tollens. Can you do something like this? Could you come up with an example like this? Yeah. I can make it an upload, so you should be able to do that. All right. Does this kind of make sense now that I've given you a real world example? So I basically want a real world example of this task. So unfortunately, you can't use the drinking example, even though it's really good. But give me an example like that would work, that would fit this idea. So now that we've got like 7 minutes left, I want to go back to some of those other arguments. So when you look at these, modus ponens makes sense, right? It does when you work through it. Modus ponens or modus tollens doesn't always make sense. And we'll talk about why that. Some people think that it should be if P, then Q, not P, therefore not Q. But it turns out that that's not correct. So here I'm going to show you 2 different deductive forms that look logical, but are not. So the first is what is called affirmation of the consequent. So that takes this form. Folks, this is not valid. If P, then Q, Q, therefore P. So we're basically, so this is, the P is what we call the antecedent, Q is called the consequent. So if we are affirming the consequent, we're basically saying Q is correct, therefore P must be correct. So here's an example. If it's an apple, if this is an apple, then it is green. This object is green, therefore it must be an apple. That's not true. There are lots of green things that are not apples, right? So here's another example, and here's why I brought the Mountain Dew. I'm giving you a real world example that makes me laugh that I looked up myself. Okay. No, it's not what I wanted. Oh, I got to move it. Okay, we'll clear annotations. So, while watching Intervention, all crackheads love Mountain Dew. Hey, I love Mountain Dew. Exactly. That is affirmation of the consequent. If you are a crackhead, then you love Mountain Dew. You love Mountain Dew. Therefore, you are a crackhead. We can obviously see this does not work. Most people consider this valid. It is not. Remember, the if does not mean if and only if. There are other possibilities out there. So this is affirmation of the consequent. So that takes the form if P, then Q, Q, therefore P. It is not valid. You can very easily think of counterexamples of people who love Mountain Dew and are not crackheads. This is the hardest stuff I've tried. That and that Monster Energy drink at the review session that y'all warned me away from. I think you were worried I was about to go down a slippery slope to bang or something like that. Like the energy drink market is ridiculous. You know, back in my day, we just had Red Bull and that was it. And we drank that because it tasted like a strawberry sour punch. Blech. Now there's all kinds of energy drinks. It's a madhouse. All right. So here's another example and we'll finish with this. The other one is called the denial of the antecedent. So this takes the form of as follows. If P, then Q, not P, therefore not Q. So here's an example of that. If you are a ski instructor, then you have a job. You are not a ski instructor. Well, that's great. I didn't realize I didn't have a job standing up front here teaching people. So if you are a ski instructor, you have a job. If P, then Q. You are not a ski instructor, not P. Therefore, you do not have a job, not Q. So again, this premise does not say that if and only if you are a ski instructor that you have a job. There are plenty of people that have jobs that are not ski instructors. So again, this one looks like it's valid, but it isn't. So here's another example. If it is an apple, then it must be green. It is not an apple. Therefore, this object is not green. Again, there are lots of things that are green that are not apples. Do you kind of see how this works when we walk through it? I know, fun, right? You could be taking logic and learning this all the time. You're like, that's too much. Wait until we get into syllogisms on Friday. All right, everybody good? Okay, how about one more slide and we call it a day? All right. So here's what's kind of interesting. So in a study by Marcus and Rips back in 1979, they actually looked at different conditional inferences to see what people recognized as valid and not. And here's what we find. In general, most people get modus ponens. If P, then Q, P, therefore Q. It's pretty straightforward. Over almost 100% of people correctly identify that as a valid argument. They have more trouble with modus tollens. But what's interesting is that we do have a sizable percentage, about 40%, that assume that affirmation of the consequent, if you're a crackhead, you love Mountain Dew, therefore you're a crackhead. So affirmation of the consequent is valid. We do also have a sizable proportion that believe that denial of the antecedent is valid. Now, it's a small percentage, but part of the reason this happens is because we assume that the if means if and only if. When we say if, that means there are other possibilities that are out there. When we say if and only if, we're saying that there are no other possibilities. So make sure that your if is your if and not your if and only if. All right, and with that, I urge you to take your only if out of class because we are done for the day. Let me know if you have any questions on the WASN task, now that you know how to do it, and I will see you here on Friday. Have fun.